You have been lied to since the moment you were old enough to look up, not maliciously, not even knowingly, but it happened all the same. In movies where a ship leaps between star systems in the space of a jump cut, in television shows where a captain orders warp 9 and the stars smear into streaks of light, in 1,000 quiet promises that somewhere, someday, physics would bend just enough to let you outrun the dark. You were told that the only thing standing between humanity and the stars was time, better engineers, better materials, a few more centuries of trying. That promise is a corpse, and tonight, you're going to watch it die. Because somewhere in a filing cabinet of theoretical physics, there is a real equation. Not science fiction, not fan speculation, an actual peer-reviewed solution to Einstein's field equations. That describes a way to move faster than light without technically breaking the speed limit. It has a name. It has a shape. It has captured the imagination of physicists, engineers, and dreamers for over 30 years. And it will almost certainly never fly. Not because we're not smart enough, not because we haven't tried hard enough, but because the universe itself, at its most fundamental level, appears to have been built with a lock on this particular door, and the key it demands may not exist anywhere in reality. This is the story of the warp drive, and it is not a story about triumph. Let's shatter the illusion first, because you need to understand what you actually believed before you can understand what's about to replace it. You probably think of warp drive the way you think of the airplane, or the rocket, or the submarine, as an engineering problem. Hard, yes. Expensive, certainly. But fundamentally a matter of when, not if. Humanity split the atom. Humanity put a permanent laboratory in low Earth orbit. Humanity flung a piano-sized, nuclear-powered robot onto the surface of Mars and stuck the landing using a literal sky crane. Surely, given enough centuries, we solve this too. Here is the problem with that comfort. Warp drive isn't hard in the way a rocket is hard. A rocket is hard because you need better metallurgy, more efficient fuel, more precise guidance systems. All things that exist in nature and simply need to be refined, combined, and scaled. Warp drive, in its only currently known theoretical form, requires something that has never once been observed to exist in the macroscopic universe in the quantities needed: negative energy. Matter with, in effect, less than nothing mass energy. Not antimatter. Antimatter is normal, positive energy matter with an opposite charge, and we've made it in laboratories. This is something stranger, something that, in the tiny, fleeting quantities where it has been glimpsed at all, appears for a fraction of an instant and vanishes, bound by rules that seem almost personally engineered to prevent you from ever collecting enough of it to matter. In 1994, a Mexican theoretical physicist named Miguel Alcubierre sat down and asked a deceptively simple question. Does Einstein's general relativity, the same theory that says nothing can outrun a beam of light, technically forbid faster than light travel? He found a loophole, not in the speed limit itself, but in the space around it. Alcubierre proposed a bubble, a pocket of ordinary, flat space-time wrapped inside a wave. Behind the bubble, space-time would expand, stretching the fabric of the universe itself outward, pushing the destination closer. In front of the bubble, space-time would contract, collapsing the distance ahead like a rug being gathered up under your feet. The ship inside the bubble would never move relative to the space immediately surrounding it. It would sit still, motionless, comfortable, while the universe did all the moving. No local violation of relativity, no object accelerating past light speed, just the ground itself sliding out from underneath the finish line and rushing up to meet you. It is, without exaggeration, one of the most beautiful pieces of theoretical physics ever produced. It is also, in its original form, a monster that would require converting the mass energy of an object roughly the size of the planet Jupiter into pure negative energy just to move a shuttle-sized craft. Later refinements shaved that number down, from planetary to stellar to, in some optimistic calculations, merely absurd rather than impossible. But every single one of those refinements still depends on a substance that, as far as any experiment on Earth has ever confirmed, cannot be manufactured, stored, stabilized, or shaped into the configuration the mathematics demands. You are not looking at an engineering gap. You are looking at a physics gap. And physics gaps do not close with time and money the way engineering gaps do. They close, if they close at all, only when the universe itself turns out to be different from how we currently understand it. So tonight, we are not here to dream. We are here to look, honestly and completely, at every piece of what the warp drive would actually require. The exotic matter, the impossible energies, the causality violations lurking behind the curtain, and a discovery in 2012 that revealed something far more literal and far more lethal waiting at the front edge of that beautiful bubble. Something that would turn the ship you're riding in into a coffin the instant you tried to stop. We are going to walk through 30 years of humanity's most brilliant minds trying to build a door out of pure mathematics. And we are going to find out, piece by piece, equation by equation, why that door may be permanently, physically, catastrophically locked. Because before you can understand why the stars might stay forever out of reach, you first have to understand exactly how close and how far we actually got. To understand why the universe fights back against the warp drive, you first have to understand the one piece of it that isn't fiction. Because negative energy is real. It exists. It has been measured in a laboratory with instruments precise enough to detect forces smaller than the weight of a single bacterium. And that fact is both the reason the warp drive isn't pure fantasy, and the reason it will very likely never be anything more. In 1948, a Dutch physicist named Hendrik Casimir predicted something that sounds like a trick of the light. Take two metal plates, place them parallel to each other, closer together than the width of a human hair, separated by a gap measured in mere nanometers. Put them in a perfect vacuum, empty of all matter, all light, all heat. Classical physics says nothing should happen. The plates should simply sit there, inert, in a void with nothing between them to push or pull. But the vacuum of space is not actually empty. Quantum mechanics insists that even in the absence of all matter, a roiling static of virtual particles flickers in and out of existence. Pairs of particles and antiparticles born from nothing, annihilating each other within a fraction of an instant, a permanent, invisible foam bubbling beneath the surface of reality itself. Between two closely spaced plates, only certain wavelengths of this quantum foam can fit, the way only certain notes fit inside the length of a guitar string. Outside the plates, every wavelength is permitted. The result is a mismatch in pressure. The vacuum outside pushes harder than the vacuum in between. The plates get shoved together by nothing, by less than nothing. The space between them carries a lower energy density than empty space itself is supposed to have, lower than zero. In 1997, physicist Steve Lamoureux at Los Alamos National Laboratory measured this force directly, using a torsion pendulum sensitive enough to detect forces in the piconewton range, a trillionth of a newton, and confirmed Casimir's prediction to within 5% of theoretical precision. Negative energy density was no longer a mathematical curiosity buried in a 1948 paper. It was an observed, repeatable, laboratory-confirmed fact of nature. This is the moment you need to sit with, because it means Alcubierre wasn't building his warp bubble out of nothing. He was building it out of something that had already been caught once in the smallest possible trap science could construct. The Casimir effect proves that the universe permits negative energy density to exist, and that single permission slip is the entire reason warp drive research didn't die quietly in a drawer in 1994. It's the reason NASA funded studies on it. It's the reason it still gets serious treatment in journals like Classical and Quantum Gravity, the very publication that ran Alcubierre's original paper. But here's where the hope curdles. The amount of negative energy produced between two Casimir plates is almost too small to comprehend. We're talking about forces you could not detect without instruments built specifically, exquisitely, for that single purpose. To bend spacetime the way Alcubierre's metric requires, you would need negative energy densities, not trillions of times larger, but scaled up by factors that dwarf the total mass energy of visible matter in the observable universe, at least in the original 1994 formulation. Alcubierre had proven the door was real. He had not proven it could ever be opened wide enough for a ship, or a person, or a single grain of sand to pass through. Let's put the geometry itself in front of you, stripped of jargon. Picture space-time as a rubber sheet, stretched taut, with a marble resting on top representing your ship. Normally, to move the marble, you'd have to push it, accelerate it, apply force directly to it, obey Einstein's speed limit the entire way. What Alcubierre proposed instead was reaching underneath the sheet. Behind the marble, you grab the rubber and stretch it outward, expanding the distance between the marble and everywhere it's been. In front of the marble, you gather the rubber inward, crumpling the distance between the marble and everywhere it's going. The marble itself never moves an inch across the sheet's local surface. It just sits inside its own private pocket of undisturbed rubber, while the sheet itself does something extraordinary around it, stretching and compressing in a traveling wave, carrying the marble along like a piece of driftwood riding a wave through the ocean rather than swimming through it. This is why warp drive is technically legal under general relativity. Einstein's speed limit only governs how fast an object can move through space. It says nothing at all, about how fast space itself is permitted to move. And space has, in fact, already broken that limit on a scale that makes anything a human engineer could design look microscopic by comparison. In the first fraction of a second after the Big Bang, during the epoch known as cosmic inflation, physicists believe the universe itself expanded from smaller than a single atom to roughly the size of a grapefruit in less time than it takes light to cross that same grapefruit today. An expansion rate that, translated into velocity, vastly exceeds the speed of light. Nothing was moving. Space itself was simply growing, faster than light could ever travel across it. That is the loophole. That is the entire, elegant, terrifying premise of the warp drive. Convince a small pocket of the universe to do, deliberately and on command, what the entire universe once did by accident in its first violent instant of existence. The Casimir effect tells you the ingredient is real. Cosmic inflation tells you the mechanism is real. What neither one tells you, what no experiment on Earth has ever come close to answering, is whether you can ever, by any means, produce enough of that ingredient, shaped in exactly the configuration the mathematics demands, without the entire scheme collapsing under its own impossible weight. For 18 years, the exotic matter problem sat there like a locked vault door with no combination in sight. Then, in 2012, a NASA physicist named Harold Sonny White did something nobody had thought to try. He didn't invent new physics. He didn't discover a new particle. He simply changed the shape of the bubble. Alcubierre's original geometry, the one published in 1994, called for a warp bubble shaped like a thin, flat ring, a donut of curved spacetime wrapped tightly around the ship with sharp, narrow walls where all the exotic matter had to be crammed. White ran the numbers again, using a thicker, more rounded bubble geometry, one that spread the required negative energy across a broader, gentler curve instead of squeezing it into a razor-thin shell. The result was staggering. By softening the bubble's walls and oscillating the geometry over time rather than holding it rigid, White calculated that the exotic matter requirement could, in theory, drop from a mass on the order of Jupiter down to something closer to the mass of a car. Some versions of the calculation suggested a spacecraft weighing roughly 1,000 kilograms could be pushed to a superluminal speed using an amount of exotic matter equivalent to a few hundred kilograms. This was the moment warp drive stopped being a punchline in physics departments and became, briefly, something you could put in a NASA presentation without people snickering. White even built a small tabletop experiment at Johnson Space Center called the White-Jude Warp Field Interferometer, an attempt to detect whether a tiny, laboratory-scale disturbance of spacetime could be measured using laser interferometry, the same fundamental technique that would later detect gravitational waves at LIGO. It never produced a positive result. It was never expected to. Not really. The sensitivity required was, and remains, laughably far beyond what a benchtop laser setup could achieve. But it signaled something important. For a brief window in the early 2010s, warp drive research had a foothold, however small, inside a legitimate government space agency. And then the math got harder again. Because a smaller mass requirement is not the same thing as a survivable one. Here's where the story turns dark, because this is where the physics stopped being merely difficult and started becoming actively hostile. In 2021, physicists Eric Lentz and, separately, teams re-examining the warp shell concept found something the original 1994 paper had glossed over: the front wall of the Alcubierre bubble. The leading edge, where contracting spacetime meets the undisturbed universe ahead of the ship, doesn't behave like a gentle boundary. It behaves like a blade. Picture it. Your ship sits motionless inside its bubble of flat, comfortable spacetime, being carried along as the universe folds and unfolds around you. From your perspective, nothing is happening. No acceleration, no g-forces. You could be sipping coffee. But every single photon, every stray hydrogen atom, every speck of interstellar dust that happens to lie in your bubble's path gets swept up at the leading wall and compressed into that razor-thin boundary layer, accumulated frame after frame as your bubble eats through the universe ahead of it. Because the bubble itself never slows down relative to the space immediately behind it, none of that accumulated energy has anywhere to go. It just piles up, faster than light, moving faster than light, colliding against a wall made of curved spacetime that is, itself, moving at a velocity the accumulated particles cannot outrun. The calculations suggest that when the ship finally decelerates, when the bubble collapses back down to subluminal speed, releasing everything trapped in that leading wall, the result would be a blast of high-energy particles directed forward with a magnitude that dwarfs anything a gamma-ray burst delivers to nearby star systems. Every world in the destination system, annihilated in the instant of arrival by the accumulated debris of the entire journey, unleashed in a single cataclysmic pulse. The warp drive doesn't ferry you gently to your destination. In its most literal mathematical formulation, it arrives as a weapon. Every voyage ends the same way. Every voyage began millions of years ago in some corner of physics nobody had bothered to check, as a funeral pyre for whatever was waiting at the far end. This is not a minor engineering flaw you patch with a software update. This is a structural feature of the geometry itself, a direct, unavoidable consequence of the way an Alcubierre bubble interacts with the causal structure of the universe it's plowing through. Some theorists have proposed workarounds, perhaps a bubble that never fully collapses, that decelerates so gradually the front wall accumulation never reaches lethal density, Perhaps a warp shell geometry, distinct from Alcubierre's original ring, that redistributes the problem instead of eliminating it. None of these workarounds have been shown to actually solve the underlying instability. All of them, so far, simply relocate the catastrophe to a different stage of the journey. And even if you could somehow neutralize the front wall problem, even if you found a geometry gentle enough to survive its own arrival, you still haven't manufactured a single gram of the exotic matter required to power it. Sonny White's most optimistic revision still calls for negative energy density in quantities no experiment on Earth has ever produced outside the infinitesimal, fleeting confines of a Casimir cavity. You would need to hold that exotic matter in a stable, controlled configuration, shaped precisely enough to maintain bubble geometry across the full duration of an interstellar crossing. For years, potentially decades, without so much as a flicker of instability, because a flickering warp field isn't a slower spaceship. It's a spaceship that stops existing. So this is where the story actually stands, stripped of the optimism of documentaries that stop the analysis one step too early. We know negative energy is real. We know the geometry can, on paper, be softened into something merely astronomical instead of literally impossible. And we know, now, that even a perfect engineering solution to the exotic matter problem still leaves you holding a spacecraft that annihilates its own destination on arrival, a monster wearing the shape of a miracle. The universe did not forget to give you an exit. It built one, carefully, and then wired it directly into the guillotine. There is a second monster hiding inside the warp bubble, and it has nothing to do with energy at all. It has to do with time. In 1994, when Alcubierre published his metric, a young physicist read it and immediately understood something that should have ended the conversation right there. His name was Alan Everett, and in 1996, he demonstrated that any spacetime capable of carrying a ship faster than light could also, with a small modification, be turned into a time machine. Not metaphorically, not in some speculative, hand-wavy sense. Mathematically, rigorously, inescapably. Here's the mechanism, and it's worth sitting with because it's stranger than anything in the energy problem. Imagine two warp-capable ships. One departs Earth and travels to a star system 20 light-years away, arriving, thanks to the bubble, in what its onboard clock measures as a matter of weeks. From the perspective of an observer on Earth, that ship has, in a very real sense, outrun light itself across that distance. Now imagine a second ship, cruising nearby at a significant fraction of light speed, watching the first ship depart. Because of the way relativity treats simultaneity, because at the same time is not a fixed, universal concept but depends entirely on how fast you're moving. That second observer, moving fast enough in the right direction, would perceive the first ship arriving at its destination before it departed Earth. Not as an illusion, not as a trick of light delay, as a genuine violation of cause and effect baked directly into the structure of relativity itself. Chain enough of these warp trips together, bouncing signals or ships between different reference frames moving at different velocities, and you don't just get faster than light travel. You get a closed loop, a ship that can, in principle, arrive at its own point of departure before it left. A message that reaches its recipient before its sender wrote it. The physics literature has a chillingly clinical name for this: the tachyonic antitelephone, a communication device that lets you receive a reply before you've sent the question. It is the mathematical skeleton key hiding behind almost every version of faster-than-light travel ever proposed, whether by warp bubble or wormhole or any other geometry general relativity permits. If you can outrun light under the right conditions, you can outrun causality. And once causality breaks, so does the grandfather paradox, so does the entire logical architecture that allows the universe to make sense from one moment to the next. Stephen Hawking looked directly at this problem in 1992, 2 years before Alcubierre's paper even existed, and proposed something he called the chronology protection conjecture. Hawking's argument wasn't just philosophical squeamishness about paradoxes. It was a physical claim, backed by calculation, that the laws of physics themselves, at the quantum level, conspire to prevent closed time-like curves from ever actually forming. His reasoning centered on what happens to the quantum vacuum fluctuations we discussed earlier, the same virtual particle foam behind the Casimir effect, as a region of space-time approaches the threshold of becoming a time machine. Hawking calculated that as you get closer and closer to closing a causal loop, those vacuum fluctuations would build toward infinite energy density right at the boundary, a runaway feedback effect that would destroy the very structure attempting to create the time machine before it could ever complete the loop. The universe, in Hawking's formulation, doesn't need to actively forbid time travel with some cosmic rulebook. It simply makes the price of attempting it fatal, automatically, as a side effect of quantum mechanics defending its own consistency. He put it more bluntly in a public lecture years later. There is now fairly good evidence that chronology protection is a law of physics, even though we don't yet understand exactly why it's true. He was joking, in his way, that this must be why we've never been overrun by tourists from the future. But underneath the joke was a serious wager, one he made in a 1990 paper with fellow physicists, half in earnest, that a working chronology protection theorem would eventually be found within the framework of a complete theory of quantum gravity, and that any space-time geometry attempting to create closed time-like curves would prove physically unstable, mathematically self-destructing before it could ever be switched on. This is the second lock on the door, and it is arguably more damning than the first. The exotic matter problem, brutal as it is, remains at least conceivable to solve. An engineering and physics challenge that some future breakthrough in quantum field theory might, in principle, chip away at. But the causality problem is different in kind. It suggests that faster-than-light travel isn't merely difficult because we lack the materials. It suggests that the universe may treat the mere possibility of FTL travel as an existential threat to its own logical consistency, and responds by making the attempt self-annihilating at exactly the moment it would otherwise succeed. Some physicists have tried to find a middle path. They've proposed that warp drives might be permissible so long as they're constrained to never exceed the light cone established at the moment of construction, meaning you could build a warp drive after a civilization already exists at a destination star, using it to visit places already causally connected to you, but never use it to reach somewhere fundamentally new, somewhere that couldn't already. In principle, exchange a light speed signal with your point of origin. It's an elegant patch. It's also a devastating admission. Even in its most careful, causality-respecting form, the warp drive stops being a tool for genuine exploration. It becomes, at best, a faster shuttle between destinations humanity would need centuries of ordinary light-speed-limited contact to establish in the first place. The frontier shrinks to the size of what you already knew was there. You came into this chapter hoping for a loophole in a speed limit. What you found instead was a universe that appears to have wired a second, deeper law directly behind the first one. Not, thou shalt not exceed light speed, but something closer to, thou shalt not unmake the order in which things happen. And unlike the negative energy problem, this isn't a matter of scale. You cannot brute force your way past causality with a bigger reactor or a more efficient bubble geometry. If Hawking was right, the universe doesn't argue with you about this one. It simply ends the experiment at the exact moment the experiment would have mattered. In 2012, 3 physicists at the University of Sydney, Brendan McMonagle, Geraint Lewis, and Philip O'Byrne, sat down not to ask whether the warp drive could be built, but to ask a much colder, much more practical question. If it could, what would actually happen to the space directly in front of it while it traveled? What they found didn't just complicate the warp drive. It suggested that even a fully functional Alcubierre bubble, with all its exotic matter problems magically solved, might be a death sentence for anyone standing at your destination, and possibly for you. Here's the mechanism, and it's worth walking through slowly, because it's one of the most quietly horrifying pieces of physics in this entire story. As a warp bubble moves through interstellar space, it doesn't travel through a perfect vacuum. Real space is thin, but it isn't empty. It's populated by stray hydrogen atoms, cosmic dust, the occasional high-energy particle flung out by some distant supernova millions of years ago. Under ordinary circumstances, a ship moving through this thin soup at sublight speed simply plows through it, the way a car drives through light rain. Unpleasant at extreme speeds, but manageable, survivable, something you shield against. The Sydney team modeled what happens to these particles when a warp bubble sweeps through them. Because the bubble represents an extreme, rapidly changing distortion in spacetime's curvature, expanding space behind it, contracting space ahead of it. Any particle that drifts into the region directly in front of the bubble doesn't get gently pushed aside. It gets caught, trapped in the region of extreme curvature at the bubble's leading edge, unable to escape the geometry, accumulating there as the ship continues forward, gathering more and more particles the longer and farther the journey continues. Think of it like the bow wave in front of a ship's hull, except instead of water, you're pushing forward a slowly growing, increasingly energetic cloud of trapped matter, compressed into the sharply curved space at your ship's leading edge. Here's the part that turns an inconvenience into a catastrophe. That trapped matter doesn't just sit there harmlessly. According to the team's calculations, the particles accumulating in the region of extreme space-time curvature would be boosted to extraordinarily high energies by the interaction with the warp field itself. And the moment the ship decelerates, dropping out of warp at its destination, that entire accumulated cloud of trapped, blue-shifted, high-energy particles would be released in a single, instantaneous burst. Not a gentle dispersal, a discharge. The paper's own conclusion states it plainly. Any crew and anything at the destination directly ahead of the bubble would be exposed to this burst. A wave of gamma rays and high-energy particles intense enough to destroy the ship itself and anything positioned in front of it, including, potentially, the very destination you spent your journey trying to reach. Think about the cruelty of that geometry for a moment. The entire promise of the warp drive is that the crew inside the bubble is protected, untouched by the crushing tidal forces and lethal accelerations that would obliterate a human body if you tried to actually accelerate to those speeds conventionally. The bubble is supposed to be a sanctuary, a still, calm pocket of ordinary physics carrying you across the hostile dark. And it may well succeed at that, precisely as advertised, right up until the moment you arrive. Because the very act of stopping, of collapsing the bubble at your destination, could release a weapon of your own accidental making, a directed burst of radiation aimed squarely at whatever lies ahead of you. You could cross the galaxy in perfect safety and annihilate the planet you were traveling to see the instant you tried to say hello. Some physicists have since pushed back on the severity of this specific result, arguing that the magnitude of the effect depends heavily on the particular warp metric used, the density of the interstellar medium along the route, and details of bubble geometry that remain unsettled. This is real, ongoing scientific debate, and it's not resolved. But the core finding has held up under scrutiny in the years since. Even a perfect warp bubble, one where every exotic matter problem from the last 4 sections of this story has been magically solved, appears to generate its own lethal radiation hazard as an unavoidable byproduct of the geometry itself. Not a flaw in the engineering, but a consequence baked into the shape of curved spacetime interacting with the thin scatter of particles that fills the space between stars. This is what makes warp drive different from every other dangerous technology humanity has ever tamed. A nuclear reactor is dangerous because of how you build it. Shield it properly, control the reaction, and the danger becomes manageable, survivable, routine, as thousands of reactor years of safe operation worldwide have proven. But this radiation hazard isn't a flaw in a specific design you could engineer around with better shielding or a smarter bubble shape. It appears to be a structural consequence of the geometry itself. Space-time curvature interacting with ordinary matter in a way that concentrates energy no matter how carefully you design the container. You cannot shield against a weapon built into the physics of your own vehicle, and so you arrive at a genuinely strange place in this story. Even if every energy problem from the previous chapters vanished tomorrow, even if some undiscovered field of physics handed humanity an inexhaustible supply of stable, macroscopic negative energy, solved the quantum inequality, and made the Alcubierre bubble buildable with tools no more exotic than a sufficiently advanced factory, the ship you built might still be lethal by its very nature. Not lethal because it fails. Lethal because it works exactly as designed, and the design itself carries a hidden cost that no refinement of the metric has yet managed to fully erase. This is the moment in the story where you start to feel the shape of something larger than a single failed technology. Because warp drive isn't the only faster-than-light concept physicists have proposed. There's another one, older, in some ways stranger, and tied to a problem so fundamental that Einstein himself worried about it: the wormhole and the ancient, merciless law of cause and effect it threatens to break wide open. There is a second door to faster-than-light travel, and it doesn't ask you to outrun space at all. It asks you to skip it entirely. In 1935, Einstein and physicist Nathan Rosen were examining the mathematics of black holes when they noticed something strange buried in the equations, a solution that seemed to connect two separate points in spacetime through a kind of tunnel, a bridge between two black hole-like structures. They called it, appropriately, the Einstein-Rosen bridge. At the time, it was considered a mathematical curiosity, not a real physical possibility. The bridge in their solution pinched shut instantaneously, faster than light itself could cross it, sealing before anything, even a photon, could pass through. A door that closes faster than you can walk through it isn't a door. It's a coffin lid. For over 50 years, that's where wormholes stayed. An elegant footnote, a mathematical ghost. Then, in 1988, physicist Kip Thorne received an unusual phone call. Carl Sagan was writing a novel, later titled Contact, and needed his protagonist to travel to the star Vega without violating the laws of physics as he understood them. Sagan asked Thorne, one of the era's leading experts on general relativity, whether there was any legitimate physical mechanism that could make it work. Thorne, together with his student Michael Morris, took the challenge seriously enough to publish the resulting analysis in the American Journal of Physics under the title Wormholes in Spacetime and Their Use for Interstellar Travel. It remains one of the strangest origin stories in the history of theoretical physics. One of the most cited papers on traversable wormholes exists because a science fiction novelist needed a plot device to survive peer review. What Morris and Thorne found was this: a wormhole could, in principle, remain open long enough for something to pass through, but only if its throat, the narrow connecting passage between two distant points in spacetime, was held open by a specific kind of matter. Matter with negative energy density, the exact same substance, the exact same physical requirement that haunts the warp drive. Notice what's happening here. Two completely different approaches to faster-than-light travel. One bending space around a ship like a wave, the other punching a tunnel directly between 2 points. arrived independently at the identical, impossible ingredient. This isn't a coincidence born of two physicists happening to like the same idea. It's a signal. When two unrelated solutions to the same problem both require an ingredient nature seems reluctant to provide in bulk, you start to suspect the universe isn't withholding a technology. It's withholding a category of technology, and it's doing so consistently from every conceivable angle you approach it. Picture the difference this way. The warp drive is like carrying your own patch of solid ground with you across a swamp, letting the swamp compress and expand around your feet as you go. The wormhole is like folding a map in half and punching a pencil straight through both layers, so a point that was 1,000 miles away on the flat page becomes a fraction of an inch away once the paper is folded. Distance, in this picture, was never real to begin with, just an accident of how the paper happened to be lying flat. Fold it correctly, and the miles vanish. It's a gorgeous image. And like the warp bubble, its beauty conceals a nightmare, one that has nothing to do with energy requirements at all. It has to do with time. Here's the mechanism, and it comes directly out of relativity itself, not speculation layered on top of it. Imagine you have a stable, traversable wormhole with two mouths. Call them mouth A and mouth B, initially sitting side by side in the same location, ticking through time at the same rate. Now take mouth B, load it onto a spacecraft, and accelerate it to a significant fraction of the speed of light. Send it on a long journey and bring it back to rest beside mouth A. Special relativity tells us exactly what happens during that trip: time dilation. The traveling mouth, having spent its journey moving at extreme velocity, will have experienced less elapsed time than the mouth that stayed behind. The same effect confirmed repeatedly using atomic clocks flown on aircraft and satellites. The same effect that keeps GPS satellites correctly synchronized only because engineers account for it. When mouth B returns, it might read a date years earlier than mouth A, even though both mouths exist in the same present moment, side by side, connected by a throat that runs straight between them. Step through mouth A, and you emerge from mouth B in the past. Not metaphorically, not through some story trick. According to the actual mathematics of general relativity, a wormhole with mouths in relative motion becomes, structurally, a time machine. This isn't a bug discovered later by skeptics trying to poke holes in the concept. It falls directly out of the same equations that make the wormhole traversable in the first place. You cannot have the tunnel without also, eventually, having the clock that runs backward. And a time machine is not a convenience. It's a paradox generator. Step through. Prevent your own grandfather from meeting your grandmother, and you unravel the logical structure of causation itself, the principle, more fundamental to physics than almost anything else, that causes must precede their effects, that the universe unfolds in one direction and does not permit you to reach back and unwrite the very history that produced you. Physicists have spent decades trying to resolve this. Igor Novikov proposed what's now called the self-consistency principle, the idea that the universe simply would not allow paradox-generating actions to occur, that any attempt to alter the past would be met with some intervening event preventing the contradiction, the same way a pool ball, thrown back through a wormhole to strike its earlier self off course, mysteriously always missed by exactly the amount needed to preserve the shot that sent it back in the first place. It's an elegant patch. It's also, many physicists suspect, precisely the kind of forced correction you'd expect from a universe actively defending itself against exactly this exploit. The chronology protection conjecture again, wearing a different mask, showing up at a second, entirely independent door, and finding it just as firmly locked. In 1992, Stephen Hawking sat with this exact problem. A wormhole that becomes a time machine the moment its two mouths start moving relative to each other, and asked a question with teeth. Does nature actually let this happen? or does something step in first? His answer became one of the most quietly ominous papers in modern physics, titled simply Chronology Protection Conjecture. Hawking's proposal wasn't just that time travel was difficult or exotic. It was that the laws of physics appear to actively conspire against it. That just as a closed time-like curve is about to form, just as a wormhole's two mouths approach the configuration that would let you walk into your own past, something in the underlying quantum structure of space-time steps in and destroys the mechanism before it can complete. Here's what he found. As a wormhole throat approaches the threshold of becoming a time machine, as the two mouths drift closer to the exact relative motion needed to connect different moments in time, quantum field theory predicts that vacuum fluctuations passing through the throat would begin circulating through it endlessly, looping back through the wormhole again and again before that critical threshold could ever be crossed. Each loop adds more energy. The energy density inside the throat, instead of settling into the stable configuration needed to keep the wormhole open, spikes toward infinity, right at the exact moment and the exact location the time machine would activate. The mathematics suggests the wormhole would violently collapse or be torn apart by this runaway feedback loop, precisely when it mattered most, precisely at the instant the paradox would have become physically real. Sit with the elegance and the cruelty of that mechanism for a moment. It isn't that time travel is merely difficult, the way interstellar distances are merely difficult, or that it requires resources merely difficult to acquire. It's that the universe appears to have a self-destruct sequence wired directly into the geometry, one that triggers automatically, with no external intervention required, the instant the dangerous configuration begins to form. Like a fuse box that blows itself the moment a current threatens to overload the whole house. Except this fuse box is built into space-time itself, and it seems to know, in advance, exactly which currents to fear. This is, admittedly, still conjecture. Hawking's own paper is honest about its incompleteness, and physicists have spent the decades since debating whether the effect is truly universal or whether some exotic configuration might slip past it. Some theoretical work in the years following found narrow scenarios where the runaway energy buildup might be avoided under very specific, very artificial conditions. None of it has produced a working counterexample robust enough to overturn the conjecture. And notably, this is now the third independent line of physics. The Ford-Roman quantum inequality choking off warp bubbles, the destination-annihilating radiation burst found by the Sydney team, and now chronology protection strangling wormholes at the exact threshold where they become useful for time travel, all converging on the same unsettling pattern. Every path toward faster-than-light travel that theoretical physics has produced comes bundled with its own, structurally embedded failure mode. Not a coincidence of engineering. A pattern, repeating across entirely unrelated mathematical approaches, each one independently discovering its own version of a lock. There's a term physicists sometimes use, half jokingly and half seriously, for this recurring phenomenon: cosmic censorship. Roger Penrose coined the original version of the phrase in a different context. The idea that the universe hides the genuinely paradoxical, infinitely dense singularities at the centers of black holes behind event horizons, ensuring the raw, physics-breaking mathematics never becomes visible or reachable from outside. Chronology protection reads like an extension of that same instinct, applied not to singularities but to causality itself. The universe doesn't just hide its most dangerous mathematics. It appears to actively prevent that mathematics from ever becoming physically operative in the first place. If this is correct, and it remains an open question, not a settled law, then faster-than-light travel isn't simply hard the way a mission to Mars is hard. It's forbidden the way a perpetual motion machine is forbidden, not because we lack the engineering skill to build one, but because the very laws that would need to permit its operation are the same laws that guarantee its impossibility. You cannot build a machine that violates the second law of thermodynamics, no matter how many centuries of technological progress you're given, because the prohibition isn't a gap in your toolkit. It's a statement about what the universe fundamentally allows to happen. Chronology protection and the mounting circumstantial evidence around it increasingly reads the same way. Now step back and notice the shape of everything you've learned so far. Warp drive needs negative energy in quantities the quantum inequality seems built to forbid. Wormholes need the same negative energy to stay open, and if they ever do stay open, the resulting time travel configuration seems to trigger its own destruction the instant it becomes dangerous. And even in the fantasy scenario where every one of these obstacles gets solved, infinite negative energy, a stable throat, a bubble that never collapses prematurely. The radiation hazard discovered in 2012 suggests the very act of using the technology could be lethal to whatever lies at your destination. 3 independent doors, 3 independent locks, 3 independent physical mechanisms discovered by different physicists using different mathematics across different decades, each one arriving at essentially the same verdict, not yet, and quite possibly not ever. This is where a documentary about warp drive is supposed to pivot toward hope, toward some clever workaround, some emerging idea that might slip past all 3 locks at once. And there is one candidate still standing in the theoretical literature, one that doesn't rely on the Alcubierre metric or Morris-Thorne wormholes at all, but instead reaches for a substance so exotic that most physicists doubt it exists in nature in any usable form. Matter with genuinely negative mass, not negative energy density, but negative inertial mass. A substance that would fall upward when dropped, accelerate toward you when pushed away, and behave in ways so alien to ordinary intuition that even describing it correctly requires unlearning almost everything Newton ever taught you. There is one more theoretical escape hatch, and it deserves its due before we let it go, because it doesn't need Alcubierre's bubble or Morris and Thorne's wormhole throat at all. It needs something even stranger, matter that falls upward. Negative mass is not the same thing as negative energy density, and the distinction matters enormously. The Casimir effect, the exotic matter propping open a wormhole throat, the negative energy density warping Alcubierre's bubble wall, all of that describes energy that is locally less than the vacuum's baseline, a kind of quantum-scale debt borrowed briefly from the fabric of empty space. Negative mass is a different beast entirely. It describes an object with genuinely inverted inertia, something that, when you push it, accelerates toward you instead of away. Something that, dropped from your hand in a gravitational field, would fall upward, defying not just intuition, but the entire mechanical relationship between force and motion that Newton wrote down in 1687, and that has held, without meaningful exception, for every object ever measured in the history of physics. Picture 2 objects side by side, one ordinary, one negative mass. Push them apart. The ordinary object obeys Newton exactly as you'd expect. It recoils away from the push. The negative mass object does the opposite. It accelerates toward the force pushing it, chasing the very thing trying to repel it. Now imagine placing them next to each other with no external force at all. The ordinary mass pulls the negative mass toward it, gravitationally, the way any 2 masses attract. But the negative mass, obeying its own inverted rules, gets pushed away by that same gravitational attraction rather than pulled in, and so it flees. The ordinary mass gives chase, hopelessly, forever, both objects accelerating together across the universe in the same direction, gaining speed indefinitely, bound to each other in an eternal, physics-breaking pursuit that never resolves and never slows down. Physicists call this runaway motion, and it's not a bug in the concept. It's an inevitable, mathematically guaranteed consequence of what negative mass would actually mean if it existed in bulk, stable, ordinary form. This is precisely why, in 2017, when a team led by physicist Peter Engels at Washington State University announced they had created a fluid exhibiting negative effective mass, the headlines overstated what had actually happened. The team cooled rubidium atoms to within a hair's breadth of absolute zero, creating a Bose-Einstein condensate, a state of matter where atoms lose their individual identity and behave as a single coherent quantum wave, and then used lasers to manipulate that wave's momentum-energy relationship. When they pushed the condensate, it did, in a very real and measured sense, accelerate backward, exactly as true negative mass would. But this wasn't fundamental negative mass, some new particle discovered lurking in nature. It was an emergent, effective behavior, a consequence of the condensate's engineered internal structure, present only within that carefully constructed laser trap, vanishing the instant the experimental conditions were removed. It's the physics equivalent of a hologram, a genuine, measurable optical effect produced by real light, but not proof that the three-dimensional object it depicts actually exists in your hand. No experiment in the history of physics has ever detected fundamental negative mass, a particle or field with intrinsically inverted inertia, existing independent of some artificial laboratory trap holding the illusion together. And there are good theoretical reasons to suspect none ever will. The runaway motion problem isn't just aesthetically strange. It would be catastrophically destabilizing if it existed at any meaningful scale in nature. A universe with genuine, bulk negative mass floating freely would be a universe where matter and its negative mass counterpart chase each other into ever-accelerating pairs indefinitely, converting gravitational potential energy into runaway kinetic energy without limit, a violation of energy conservation so fundamental that most physicists treat its absence in nature not as an unsolved mystery, but as something closer to a load-bearing requirement for the universe to function coherently at all. So set this door aside, gently, the way you'd set aside a beautiful blueprint for a machine that turns out to violate its own foundation. Negative mass remains a fascinating subject in condensed matter physics, genuinely useful for engineering strange fluid dynamics and studying exotic quantum behavior in the lab. But as a fuel for interstellar travel, it appears to belong to the same category as the perpetual motion machine, not merely unbuilt, but structurally incompatible with the rules that would need to govern its own existence. Which brings you, finally, to the honest tally. 3 independent theoretical pathways to faster-than-light travel: the Alcubierre warp bubble, the Morris-Thorne traversable wormhole, and hypothetical bulk negative mass, and 3 independent, structurally embedded failure modes discovered by different physicists using different mathematics, published across 5 decades of literature, none of them talking to each other, none of them designed to reach a shared conclusion, and yet all of them arriving at the same place. The quantum inequality throttles sustain negative energy density to the point of uselessness. Chronology protection appears to destroy time machine configurations at the exact threshold where they'd become dangerous. Runaway motion makes bulk negative mass energetically catastrophic and, so far, entirely unobserved in nature. This isn't 3 unlucky dead ends. It's a pattern robust enough that a growing number of physicists now treat it less as an open engineering question and more as tentative evidence for something like a genuine cosmic speed limit. Not arbitrary, not a placeholder waiting to be revised, but a structural feature of reality as fundamental as the impossibility of dividing by zero. And if that's true, if faster-than-light travel really is off the table, permanently, not for lack of trying, but because the universe itself was built without that particular door, then the question stops being, how do we build a warp drive and become something far heavier? What, exactly, are humanity's actual, physically permitted options for ever reaching another star at all? because there is still a version of interstellar travel that doesn't require breaking a single law of physics. It just requires something almost as hard to accept as impossibility itself. Patience measured not in years, but in generations upon generations, riding through a universe that offers no shortcuts, only distance and time and the slow, grinding arithmetic of speed. Let's do the arithmetic the universe actually permits, because it is, in its own way, more staggering than any warp drive equation you've encountered so far. Proxima Centauri, the nearest star to our Sun, sits 4.24 light-years away, roughly 40 trillion kilometers, or about 25 trillion miles. Voyager 1, humanity's fastest and farthest traveling spacecraft, launched in 1977, has spent nearly 5 decades accelerating through the emptiness beyond our solar system and currently moves at roughly 61,000 kilometers per hour relative to the Sun, fast enough to cross the continental United States in about 4 minutes. At that speed, Voyager 1 would need approximately 73,000 years to reach Proxima Centauri if it were even pointed in that direction, which it isn't. 73,000 years. Longer than the entire span of anatomically modern humans making art, longer than agriculture, longer than every civilization that has ever risen and fallen on Earth, stacked end to end and then multiplied several times over. This is the number that ends most conversations about interstellar travel before they even begin. But it is not, physicists insist, the final word. Because Voyager 1 was never built for speed. It was built to survive 4 decades and keep transmitting. A triumph of longevity, not velocity. The real physical limits on how fast humanity could theoretically travel, using nothing but engineering refined from technology we already understand, sit dramatically higher. And once you start climbing that ladder of speed, something genuinely strange begins to happen to time itself. In 2009, the theoretical concept of a Bussard ramjet, first proposed by physicist Robert Bussard in 1960, imagined a starship that wouldn't need to carry its own fuel at all. Instead, it would use a colossal electromagnetic scoop, potentially spanning hundreds of kilometers across, to funnel the thin scatter of interstellar hydrogen directly into a fusion reactor as it traveled, burning the very emptiness of space itself as propellant. In principle, a ramjet could accelerate continuously for years, climbing closer and closer to the speed of light, limited only by the increasing drag of the interstellar medium at extreme velocity. In practice, subsequent analysis found the drag problem worse than Bussard anticipated. The faster the ship goes, the more resistance the scoop encounters, potentially capping its maximum practical velocity well short of relativistic speeds. The concept remains a beautiful, unbuilt idea, a reminder that even our fusion-powered fantasies run into their own quieter version of a locked door. A more sobering, more grounded proposal came out of Breakthrough Starshot, an initiative announced in 2016 and backed by physicist Stephen Hawking and investor Yuri Milner. Rather than building a large crewed ship at all, the plan proposes launching a swarm of gram-scale probes, each fitted with a light sail only a few meters across, and accelerating them using a ground-based laser array delivering upward of 100 gigawatts of focused light pressure for a few brief minutes. The math suggests such a probe could theoretically reach roughly 20% of the speed of light, fast enough to cross the distance to Proxima Centauri in a little over 20 years rather than 73,000. No human passenger survives that acceleration profile, and no version of the concept currently on the table scales up to carry a crew. But it demonstrates something important. Without breaking a single law of physics, without a gram of exotic matter, humanity can already sketch a plausible engineering pathway to reach a neighboring star system within a single human lifetime. For a probe, not a person. and only if tens of billions of dollars and decades of laser infrastructure development actually materialize. For a crewed voyage, the numbers change shape entirely, because now you have to keep a human body alive, fed, shielded from radiation, and psychologically intact for a journey that no laser sail alone can shorten enough. This is where the concept of the generation ship enters. Not science fiction, but a serious subject of engineering literature since physicist and rocket pioneer Robert Goddard first floated the idea in a private, unpublished 1918 essay titled The Ultimate Migration. A generation ship accepts an uncomfortable premise from the outset. The crew that launches will not be the crew that arrives. Children will be born aboard, grow old aboard, and die aboard, never once setting foot on the destination their ancestors departed to reach. A voyage measured not in years, but in successive human lifetimes, an entire self-contained civilization sealed inside a hull, tasked with preserving enough genetic diversity, enough cultural continuity, and enough functioning technology across dozens of generations to still be capable of successfully landing a viable colony centuries after the ship's original architects have turned to dust. Consider what that actually demands. A 2002 study by physicist and engineer Marin Soljacic and colleagues estimated that a minimum viable generation ship population, accounting for genetic diversity alone, would need somewhere between several hundred and a few thousand individuals to avoid the destructive effects of inbreeding across dozens of generations. A number later refined upward by subsequent population geneticists factoring in the unpredictable pressures of accidents, disease, and resource scarcity in a closed system with no possibility of outside rescue, ever, for the entire multi-century duration of the voyage. Every calorie those people eat for hundreds of years has to be grown, recycled, or manufactured on board. Every breath of oxygen has to be regenerated in a closed loop that cannot fail, not once, not for a single day, across a timeline longer than the entire history of the United States as a nation. And even this staggering, generations-spanning undertaking is still, technically, cheating slightly less than you might think, because relativity offers one final, genuinely strange gift to anyone willing to accelerate close enough to the speed of light. Time dilation doesn't just slow the traveling wormhole mouth in a thought experiment. It applies to you, personally, aboard any sufficiently fast ship, in a way that could compress a journey lasting decades from the perspective of everyone back on Earth into something startlingly shorter from your own point of view. A real physical effect, confirmed repeatedly, that turns the brutal arithmetic of interstellar distance into something almost survivable for a single human traveler, at a cost measured not in impossible physics, but in something arguably crueler. Everyone you ever loved, growing old and dying while you barely age a day. Here is the strangest gift relativity offers you, and also the cruelest. The faster you go, the less time you personally experience. But the world you left behind keeps aging at its own unforgiving pace, with no way to pause it, slow it, or bring it along for the ride. The mechanism isn't speculative. It's been tested, repeatedly, with instruments precise enough to measure the effect directly. In 1971, physicists Joseph Haefele and Richard Keating flew commercial airliners loaded with cesium atomic clocks around the world, once eastward and once westward, then compared the elapsed time on those clocks against identical clocks that had stayed on the ground at the U.S. Naval Observatory. The airborne clocks came back reading a different elapsed time than the stationary ones. A difference of mere nanoseconds, but precisely, to within experimental error, the amount Einstein's special relativity predicted. Time dilation isn't a thought experiment confined to chalkboards. It is a measured, repeatable, engineering-grade fact. The same effect that GPS satellites must be corrected for every single day, because their onboard atomic clocks orbiting at altitude and at speed, genuinely do run at a different rate than clocks on the surface of the Earth beneath them. Without that correction, GPS positioning would drift by several kilometers within a single day. Now scale that whisper-thin effect up to something close to the speed of light, and the whisper becomes a scream. The relationship is governed by a factor physicists call gamma, and it behaves almost gently at low speeds before turning vicious as you approach the cosmic limit. At 50% of light speed, time for the traveler slows to roughly 87% of the rate experienced by those who stayed behind. Noticeable, but survivable in human terms. At 90% of light speed, that ratio collapses to roughly 44%. For every year the ship's crew experiences, more than 2 years pass back home. At 99.5% of light speed, the ratio drops below 10%. At 99.999%, a velocity requiring energy expenditures that dwarf anything humanity has